Most vision language models we use today are generative. They respond to a picture or video by producing tokens one after another, much like a large language model. This approach works, but it has two big downsides. It's expensive and slow, and it wastes a lot of effort reconstructing surface-level details that don't matter for understanding. Worse, autoregressive decoding must finish generating every word before you see the answer, which introduces latency. These limitations make current models unsuitable for tasks like live video monitoring or smart glasses. VL-JEPA, or Vision Language Joint Embedding Predictive Architecture, developed by DeLong Chen, Mustafa Shukor, and colleagues at Metafair in December 2025, is a non-generative vision language model. Instead of generating a sentence, it predicts a continuous embedding a fixed-length vector representing the meaning of the answer. This means the model learns in a latent representation space focusing on task-relevant semantics while ignoring surface-level linguistic variability. The result, higher performance with roughly 50% fewer trainable parameters than comparable token generative models. VL-JEPA is designed for efficiency. A lightweight text decoder is only invoked when a human-readable answer is needed. Because it predicts embeddings directly, VL-JEPA also supports selective decoding. It can monitor a video in real time and only translate embeddings into words when something important changes. Experiments show this reduces decoding operations by about 2.85x compared with uniform decoding. Break the architecture into its four modules. X-encoder, a vision encoder based on VL-JEPA 2, compresses an image or video into a sequence of visual embeddings. Predictor, adapted from Llama 3 transformer layers, it takes visual embeddings and a textual query, the question, and predicts the embedding of the answer. This component learns to map visual input and text into a shared latent space. Y-encoder, based on embedding Gemma 300M, it embeds the target answer into the same continuous space. Y-decoder, a lightweight text decoder that converts predicted embeddings back into natural language only when needed. Explain that the model is trained in two phases. First, it learns visual text alignment using billions of image text and video text pairs. Datacomp, YFCC 100M, Ego4D, and more in a query-free pre-training stage. And then it undergoes supervised fine-tuning on tasks like visual question answering, VQA, and captioning. During training, the objective is defined in the embedding space, info NCE loss, instead of token space, which simplifies the target distribution. Because multiple plausible answers map to nearby points in embedding space, the model doesn't have to fit disjoint token sequences. Mention that VL-JEPA can handle multiple tasks with the same architecture captioning, VQA, open vocabulary classification, and text-to-video retrieval without changing the network. Selective decoding further allows the model to monitor video streams continuously and only decode when a semantic shift occurs. Under strict zero-shot evaluation on 8 video classification datasets, the baseline VL-JEPA-based model achieved an average top-1 accuracy of 46.4%, surpassing the large PE core model 44.6% despite using less training data. On 8 text-to-video retrieval datasets, VL-JEPA-base achieved an average recall 1 of 58.4%, slightly higher than PE core's 58.1%. After supervised fine-tuning VL-JEPA-SFT, the model improved dramatically, approaching or exceeding specialist models on tasks like GQA, TallyQA, PoPay, and PoPEV2. Although some larger generative models such as Qwen2VL or LLaVA still achieve higher scores on certain datasets, VL-JEPA-SFT's results are competitive with a number of bigger models. For instance, it outperforms Instruct BLIP Flan T5XL on GQA 60.8% versus 48.4%, and matches Qwen VL Chat 7B on several benchmarks despite using only 1.6 billion parameters. Emphasize that these gains come with major efficiency benefits. Compared with traditional vision language models, VL-JEPA trains faster, requires roughly 50% fewer trainable parameters, and cuts down decoding operations by a factor of about 2.85. These attributes make it attractive for real-time applications. VL-JEPA is designed not to generate text or images, but to understand visual inputs. The model predicts abstract embeddings rather than pixel-level outputs, which makes it robust to irrelevant details like lighting or texture. Because it avoids autoregressive decoding, it excels at processing high-velocity video streams and can rapidly spot changes or answer questions about what's happening. That makes it ideal for smart glasses, robotics, surveillance, and navigation systems where latency is critical. By forcing the vision and language encoders to speak the same mathematical language, VL-JEPA produces a compact representation more usable for downstream tasks like classification and action recognition. Its predictive component also captures temporal dynamics better than contrastive models like CLIP for zero-shot text-to-video retrieval. Meta has released code and checkpoints for the JEPA family, encouraging researchers to integrate the architecture into robotics and edge devices. As analyses note, the future of vision language AI may split between generative models for creation and non-generative models like VL-JEPA for perception. Some researchers remain skeptical. They argue predicting embeddings may still be a sophisticated form of pattern matching and that VL-JEPA could overfit to visual biases rather than learning true physics. To serve as a world model, future benchmarks must test whether JEPA-based systems can predict outcomes in unfamiliar physical environments. Current evidence shows that VL-JEPA moves us closer to robust perception but doesn't yet provide full causal understanding. Also note that VL-JEPA is not a drop-in replacement for large language models. It cannot generate novel captions or imaginary videos. Its strength lies in perception and retrieval, so generative models still have a place in creative tasks. Wrap up by highlighting the significance of VL-JEPA. It marks a shift from token generative vision language models toward efficient, non-generative architectures. By predicting in latent space, VL-JEPA achieves better performance on classification, retrieval, and VQA tasks with fewer parameters and lower latency. The model's success suggests that future AI systems will likely combine generative and non-generative approaches, reserving heavy generative decoders for tasks that truly require them while using JEPA-like modules for perception and reasoning. If you enjoyed this deep dive into VL-JEPA, let us know in the comments. Don't forget to like and subscribe for more explorations of cutting-edge AI tech and science.